Elektor, and I will be co-presenting this webinar with Tim McCarthy from Microchip. Tim McCarthy is the one who put this class together, and he knows everything about our subject. So, hi Tim, how are you today?
Hi Clemens, how are you? I'm great. Thanks for the invitation to participate in this today.
No, we are very happy to have you. You are far away from me. Where are you exactly?
I'm located in San Jose, California.
Okay, that's on the other side of the US, whereas I am in France. Okay, well, this webinar is intended for people new to FPGAs. So the FPGA, that stands for Field Programmable Logic, and there are many kinds of devices. We will have a look at the basics and explain which kind you need for certain applications. This webinar is an introduction to a Microchip University course on this subject, and we will give you the link. It will be shown at the end, and we will put it also in the chat box. This webinar is divided into several blocks intended to give you an idea of the complete class. After each block, if needed, a few points will be highlighted by Tim. Don't worry if you can't follow along with the presentation, because you should take the real class anyway, when you have the time for it, as it takes about 2 hours to complete it. And when you complete the class, you get a certificate. Okay, having that said, let's get started with the presentation.
Welcome to the Getting Started with Microchip FPGAs class. I'm Tim McCarthy from the Microchip FPGA business unit located in San Jose, California. If you have never used an FPGA and are wondering if an FPGA would be suitable for your next project, this class will help you decide. In this video, I'll explain the progression of digital logic leading to the development of the first field programmable gate arrays. I'll also describe the typical architectural features of FPGAs. Early integrated circuits were called small-scale integration logic, or SSI. SSI devices implemented a single logic function, such as an AND, with fixed pin assignments. The table shows some of the many SSI devices that were available. Designers would select devices from their TTL logic databook to implement their logic equations. The limited number of gates per package often resulted in adding additional packages for just one more gate, unless unused gates were available in other packages. Here's a picture of a typical circuit board implemented using SSI devices. It took many packages to implement logic functions. In 1978, Monolithic Memories Incorporated, or MMI, introduced a breakthrough device, the Programmable Array Logic, or PAL. PAL devices have arrays of transistor cells organized in a programmable AND fixed-OR architecture. Some PAL devices have flip-flops at the outputs. PAL devices have either synchronous or asynchronous feedback from the outputs. Some PAL devices are reprogrammable. There's two types of reprogrammable PALs: UV erasable PALs that are erased by exposing them to UV light, and PAL devices based on flash technology. PAL devices provided more integration and flexibility than using SSI devices to implement digital circuits. PAL devices are sometimes referred to as programmable logic devices, or PLDs. Extending the PLD concept further produced the complex programmable logic device, or CPLD. CPLDs are made up of several simple PLDs with a programmable routing matrix to interconnect the logic blocks to each other and the I/O. CPLD devices offered 5,000 or more gates. A single CPLD could replace multiple PLD devices. One drawback of the CPLD architecture was the delay of the programmable routing matrix that was used to interconnect the simple PLD blocks. While PALs were being developed into CPLDs, a separate stream of development was happening based on gate array technology. These devices were called field programmable gate arrays, or FPGAs. FPGAs have simpler logic blocks than PALs or CPLDs, and abundant routing resources to connect the logic elements together or to the I/Os. A field programmable gate array is an integrated circuit designed to be configured after the chip is manufactured, hence field programmable. FPGAs are fine-grained devices, meaning that they contain small logic blocks called lookup tables or LUTs, along with flip-flops. The FPGA logic elements are organized in a grid similar to a gate array. Some FPGAs have hundreds of thousands of logic blocks. The I/O cells are found around the periphery of the device. FPGAs include abundant routing resources to connect the logic elements together or to the I/O cells. This is a diagram of a typical logic block in an FPGA. It consists of an N-input lookup table or LUT, whose output feeds a flip-flop. The logic block output can be the LUT output or the flip-flop output based on the configuration of the multiplexer. A LUT is a small 1-bit wide memory array with its address lines representing the inputs to the logic block and a 1-bit output. An N-LUT can implement any logic function of N inputs. This is a picture of a 4-input LUT. Configuration bits configure the LUT for the desired logic function and control the output multiplexer. In addition to LUTs and flip-flops, modern FPGAs often contain math blocks for implementing digital signal processing designs such as FIR filters, SRAM and flash memory blocks, phase lock loops or PLLs and delay lock loops or DLLs for clock frequency synthesis and phase correction, and specialized I/O supporting high-speed I/O standards and high-speed transceivers. Some FPGAs include embedded blocks such as microprocessors and peripherals, or analog blocks such as analog to digital and digital to analog converters. The two most common interconnect technologies used in FPGAs are SRAM and flash. SRAM-based FPGAs are based on static RAM technology. They're reprogrammable and volatile, meaning they have to be configured every time the device is powered. SRAM-based FPGAs often require an external boot device to hold the configuration. Flash-based FPGAs use a floating gate on a standard MOS transistor to make the interconnections in the device. Flash-based FPGAs are reprogrammable and non-volatile, meaning they don't have to be configured every time the device is powered. As a result, flash-based FPGAs don't require an external boot device. Flash-based FPGAs are also lower power than SRAM-based FPGAs. In this video, I describe the evolution of digital logic from SSI logic to PALs, to CPLDs, to FPGAs, and introduce some common features in FPGAs. In the next video, I'll explain some of the benefits of an FPGA compared to an ASIC or a general microprocessor when implementing a design. In this module, I'll describe some of the benefits of using an FPGA in a design. There are many reasons why FPGAs are popular. FPGAs can support many different applications, and they have higher density than CPLDs with a more flexible architecture and more embedded features such as memory, PLLs, and even processors. Reprogrammability minimizes risk in a product development cycle. An FPGA design can be implemented in a matter of days or a few weeks and can be modified quickly to correct bugs found in the debug cycle. Reprogrammability also allows fielded products to be updated to add additional features or correct bugs that were found after the product was released. There are different options available for implementing a digital design. Some options offer more flexibility, while other options are higher performance. Implementing a design using a microprocessor or a microcontroller provides a great deal of flexibility. A microprocessor contains all the functions of a central processing unit in a single chip. A microcontroller can be considered a simple computer with all the necessary peripherals, such as memory and timers, in a single chip. Microprocessors and microcontrollers execute programs based on the processor's instruction set. A general-purpose processor is flexible because a designer can write new code to add functionality or correct bugs, but the microprocessor architecture might not be tuned to the specific application. For example, it might take many clock cycles to perform a multiplication operation on two numbers. Compared to an FPGA, A general purpose processor has faster floating point computations, is lower per unit cost than an FPGA, and may be lower power than an FPGA. An ASIC, or application-specific integrated circuit, is a microchip designed for a specific application. ASICs are generally implemented as gate arrays, standard cell, or full custom designs. In gate arrays, the transistors and other active devices are predefined. The final metallization layer connects the transistors to implement the specific design. In standard cell designs, the mask is a custom design, but the silicon is made up from library components. This gives a high degree of design flexibility, provided that the standard library functions meet the design requirements. A full custom ASIC design is more complex than a gate array or standard cell design. Implementing a full custom design can decrease the size of an ASIC dramatically. ASICs generally incur some type of non-recurring engineering expense or NRE charges. Compared to an FPGA, ASICs can be completely customized to implement the exact design an engineer has in mind. ASICs have higher densities than FPGAs, allowing integration of several different functionalities in a single device that might require multiple FPGAs. And ASICs have lower per unit costs than FPGAs, provided that the volumes are high enough to offset the NRE charges. An FPGA offers a compromise between application-tuned performance of an ASIC and flexibility of a general microprocessor. Compared to a general-purpose processor, FPGAs have lower latency. Latency is the time between the input and the response. One of the main reasons for this low latency is that FPGAs don't depend on an operating system to implement tasks. FPGAs have flexible I/O assignments. The logic elements in an FPGA can be connected to almost any pin. Microprocessors have fixed pin assignments. The flexible pin assignment of FPGAs can simplify PC board layout. FPGAs perform parallel processing. Microprocessors execute instructions sequentially. Parallel processing allows FPGAs to respond to inputs more quickly. FPGA reprogrammability supports field updates. These updates could be more extensive than just modifying the application code. Compared to an ASIC, FPGAs offer faster time to market because the devices can be configured in the lab and modified as needed. Implementation times can be as short as a few days. FPGAs don't require any upfront non-recurring expenses like there are with an ASIC development. FPGAs have a simpler design cycle than ASICs. There's no complex floor planning or clock tree planning. And FPGAs have reduced development cycle risk. FPGAs are reprogrammable, so a bug found in the development phase can be quickly corrected. Fielded systems can be updated remotely by deploying a new bit stream. Fast time to market, parallel processing, flexible pin assignments, which simplifies board layout, reprogrammability to support bug fixes and field updates, and no NRE charges are some of the attributes that make FPGAs a good alternative to ASICs or a general-purpose processor in many digital designs.
Do you have something you would like to add to this, Tim?
I saw one question somebody asked about the cost, and it's hard for me to throw general numbers out. We'll be talking about various different FPGA families in one of the upcoming modules. An FPGA is going to cost more than an ASIC or a standard product. The die size is going to be a little bit bigger because of the routing and the interconnect technology that's used. So what you'll want to do is you'll want to decide, is an FPGA right for you? And you might need to make decisions based on factors like the NRE charges. If you designed your own custom chip, do you have volumes that offset that NRE charge that makes it worth the time and effort to go and design a custom chip? And could you use a processor, or would the FPGA let you do things faster because it's in parallel? So there are some decisions that you have to make. But in general, if you compare just the per unit cost of an FPGA either to the per unit cost of an ASIC and you didn't include the NRE, or if you looked at a processor, you'd find the FPGAs are a little bit more expensive. They have been coming down in cost. The technology has been shrinking dramatically since my first start years ago when I joined Atmel Corporation in 1993. But they still are going to be more expensive than a standard product. So you need to make a decision. Does the benefits, the flexibility, the fast time to market, and then does your volume itself justify maybe designing a custom chip and paying the NRE and so on.
Okay. I see here another question that might be interesting at this point. Others we can save for at the end. Is I can't get it completely in by Thor Berg. Will we have used CPLDs in the past, but are a bit worried about the steep knowledge training ladder to be able to take FPGAs into use? What do you think about that?
Well, most vendors and Microchips included have field application people that can work with you and offer training courses. The actual design flow to implement a design in an FPGA is kind of simple, but there are people that could help you with that, guide you through it. I know the first time through is always going to be a little bit nervous, but the flow isn't super complicated. There's steps that you might have to do if you're designing an ASIC, like clock tree planning and things that you don't have to worry about with an FPGA. So while it might be a little bit more complicated than a CPLD, it's really not that hard to master it. And like I say, there are people from all the vendors, including Microchip, that can support you as you're implementing your first design.
Okay, thank you. I
So we got
suggest.
is flash-based FPGA boot almost instant compared to non-flash? So you saw a slide that compared the interconnect technologies. The most popular type is SRAM, but SRAM is volatile. So when the device boots up, you have to configure it every single time. The flash-based devices have the floating gate where we inject a charge during programming time, and that charge stays there until you erase the device and reprogram it. So the devices are almost instant on. And when I say almost, it's because the IOs have to be configured, and we have to have a combination of an IO voltage supply plus the internal supply for the FPGA core logic to hit certain thresholds. But basically, once your power supplies hit the thresholds, the device is going to be ready to operate. So it's ready to operate much faster than an SRAM based device.
Okay, shall we continue with the presentation?
Let's see, is there any other questions
Yeah,
here?
because there are some questions that will be answered during the videos, so we can save them.
Yeah, that's probably a good idea. Yeah, why
Yeah.
don't we move on? And somebody asked quickly, what is NRE? NRE is non-recurring engineering charges. And if you design an ASIC, you typically have to pay some type of NRE charges. And if you make a mistake and have to go back and modify your design, you have to pay more NRE charges. You don't have to do that with an FPGA.
Exactly. Okay, let's let's go on to the next block.
In this video, I'll give an overview of 3 generations of Microchip Flash FPGAs. I'll start with the 3rd generation ProASIC 3, Igloo, and Smart Fusion families. These are very low density devices that can be used in place of CPLDs. After that, I'll describe the Igloo 2 and Smart Fusion 2 4th generation low density families. Then I'll describe the PolarFire and PolarFire SoC 5th generation mid-range families. All of these families are very low power, have a programming element that's immune to single event upsets or SEUs, and are live at power up. Here's a summary of the features of the 3rd, 4th, and 5th generation Flash FPGA families. ProASIC 3 and Igloo FPGAs are CPLD replacements fabricated at 130 nanometers. These families have between 100 logic elements and 35,000 logic elements, and up to 620 IOs capable of 400 megabit per second for LVDS. They have a maximum of 504 K-bits of embedded SRAM in the FPGA fabric and 1 or 6 phase-lock loops, or PLLs. Smart Fusion is a system-on-chip, or SoC FPGA, based on the 3rd generation architecture. It uses the same FPGA fabric as ProASIC 3 and adds a hard 100 MHz ARM Cortex-M3 processor subsystem with peripherals and embedded flash memory. The Smart Fusion 2 and Igloo 2 families are low-density FPGAs fabricated at 65 nanometers. SmartFusion 2 and Igloo 2 devices have up to 150,000 logic elements, up to 240 math blocks for DSP operations, and 5 megabits of embedded SRAM. There's a maximum of 574 IOs that operate at up to 667 megabits per second for DDR and 750 megabits per second for LVDS. SmartFusion 2 and Igloo 2 devices have 2, 6, or 8 PLLs and transceivers that operate between 1 gigabits per second and 5 gigabits per second. SmartFusion 2 is an SoC FPGA with a hard 166 MHz ARM Cortex-M3 subsystem with peripherals and embedded flash memory. Soft processor cores based on the RISC-V instruction set architecture are available for use in these devices. PolarFire is a mid-range FPGA fabricated at 28 nanometers. PolarFire FPGAs have up to 480,000 logic elements, 1,480 math blocks, and 33 megabits of embedded SRAM. Each PolarFire device has 8 PLLs and 8 delay lock loops or DLLs, and 56 kbytes of embedded flash memory. They have up to 584 IOs that can operate at 1600 megabits per second for DDR4 and LVDS. PolarFire transceivers operate between 250 megabits per second and 12.7 gigabits per second. Soft RISC-V processor cores and a soft Cortex-M1 processor core are available for PolarFire. Devices are available with a hard Athena Terafire crypto coprocessor for data security applications. PolarFire SoC is based on the PolarFire architecture and adds a hard 5-core 64-bit RISC-V CPU cluster with peripherals and 2 megabits of L2 cache, allowing it to support Linux and real-time applications. PolarFire SoC family members have up to 460,000 logic elements and up to 636 IOs.
Okay, as we have seen, these FPGAs can be really, really powerful. That also makes it, of course, quite complicated, I think, to use. We will have a video. We will show how to use, how to choose an FPGA, of course, which is a difficult one because of all these options. And of course, the tools. We have to explain also a little bit about the tools. Tim, would you like to add something to this?
Yeah, I think first of all, we showed different families that we offer, different families of FPGAs, and you could see that the density was going up, the IO speed was increasing, we were adding more additional internal memory. And then we also have devices that we call system on chip FPGAs that have a microcontroller and peripherals that are implemented as an ASIC, so you don't use any of the FPGA fabric at all. And that allows you to take a design where you might have a microcontroller and some other logic, maybe that you would have put in a CPLD or something. You can integrate that all into a single device, and you can even extend a set of peripherals that's available by putting more peripherals in the FPGA fabric. And we have some devices that use an ARM Cortex-M3, and then we've made a move to the new RISC-V instruction set architecture. That's actually, it shouldn't say new so much. It's been around for about 7 or 8 years now, developed at UC Berkeley. But with our PolarFire SoC family, we have a complex of 5 RISC-V cores along with an FPGA fabric. So I think you can see, and we're not the only vendor, but as the density shrink, you'll see an increase in IO speeds, you'll see more logic available, and then other features like the SoC devices with built-in processors. I see a question about the typical and maximum temperature range of microchip FPGAs. So we offer FPGAs in the commercial temperature range, which would be 0 degrees C to 70 degrees C. Industrial temperature range would be 0 degrees C to 100 degrees C. And then also some devices in particular die package combinations in the military temperature grade. So we offer devices in commercial, industrial, and military temperature grade, depending on the needs of your design that you're implementing.
Do you also have space radiation hardened devices?
Yeah, there is a question about radiation tolerant devices. We didn't go over those in the Hello FPGA, but we do have families of radiation hardened devices. We have a long history of having our devices in satellites and in spacecraft, and we have a couple of reprogrammable families for space, which is really exciting. Our original products were one-time programmable. Now we have reprogrammable products for space. So you could actually reprogram a device to extend a mission or maybe change a mission. Sometimes satellites last longer than people thought they were going to, and the mission might get extended. So you could actually reprogram the device in space. So that's a really exciting new product line for us.
Okay, well, let's move on to the next part.
Here are some criteria to help you choose the appropriate FPGA family for your next design. There are several things to consider when selecting an FPGA family, such as the number and type of I/O required, the number of logic elements in the design, the amount and type of RAM that's needed, and any hard IP blocks that are required. The number of I/Os is probably the easiest to estimate. Add the number of inputs and outputs in the design. Make sure to consider the type of I/Os that are required for the application. This includes single-ended standards like LVTTL and LVCMOS, differential standards like LVDS, and voltage reference standards like SSTL to interface to high-speed memories. Also consider specific I/O features that are required, such as Schmitt trigger inputs or hot insertion capability to allow a board to be plugged into a powered rack without disturbing the data buses. This chart shows the I/O count for Microchip's CPLD replacement families. The Igloo Nano and ProASIC 3 Nano families are available with 23 to 71 I/O in very small packages. The Igloo Plus family members have between 101 and 212 I/Os. For higher pin counts, consider ProASIC 3L, ProASIC 3, or Igloo. These families have devices with a maximum of 341 to 620 I/Os. The larger members of the ProASIC 3L, ProASIC 3, and Igloo families have I/Os that support differential I/O standards and voltage reference I/O standards for interfacing with high-speed memories. This chart shows the I/O count for Microchip's mid-range and low-density FPGA families. PolarFire has between 170 and 584 I/Os. SmartFusion 2 and Igloo 2 have between 84 and 574 I/Os. Both families support differential I/O standards and voltage referenced I/O standards. Estimating the number of flip-flops in a design is a good way to get an early estimate on the number of logic elements required. To estimate the number of flip-flops in the design, take the number of counter bits, add the number of bits for any registers in the design, such as shift registers, control and status registers, or register files, and add the number of flip-flops for any state machines in the design. A conservative estimate for state machines is to assume one hot encoding is used, where there's one flip-flop per state. The sum is the total number of flip-flops required. This chart shows the number of flip-flops that are available in the Microchip CPLD replacement families. The Igloo Plus, Igloo Nano, and ProASIC 3 Nano families have between 100 and 3,000 flip-flops. The ProASIC 3L, ProASIC 3, and Igloo families have members with up to 35,000 flip-flops. For higher density designs, consider the Microchip low-density or mid-range families. The SmartFusion 2 and Igloo 2 low-density families have between 6,000 and 146,000 flip-flops. The PolarFire mid-range family has between 109,000 and 481,000 flip-flops. If the design requires RAM, you'll need to estimate the total amount of RAM required and the type of RAM, such as 2-port, dual-port, or a FIFO. Also consider if the design requires flash memory or read-only memory. Finally, consider any specific RAM features required, such as built-in error detection and correction. You can use the RAM configurator in the Libro SoC software to build blocks of RAM to help with the estimate. The Igloo Nano, ProASIC 3 Nano, and Igloo Plus families have between 18 kilobits and 36 kilobits of RAM and are a good choice for a CPLD replacement if a small amount of RAM is needed. The ProASIC 3L, ProASIC 3, and Igloo families have up to 504 kilobits of RAM. The PolarFire mid-range FPGA family has between 7.6 megabits and 33 megabits of RAM. The PolarFire large SRAM blocks have built-in error detection and correction. The SmartFusion 2 and Igloo 2 low-density families have between 703 kilobits and 5 megabits of RAM. Consider whether the design requires any hard IP blocks, such as math blocks for DSP functions, an embedded microprocessor and the type of processor desired, analog blocks such as analog to digital or digital to analog converters, and transceivers for high-speed serial communication and the required speed. Also consider if the design requires a memory controller to interface with DDR memories such as DDR2, DDR3, or DDR4. This is a summary of the embedded features that are available in the CPLD replacement families. The Igloo, ProASIC 3, and ProASIC 3L families have 1 or 6 phase lock loops for clock frequency synthesis. The smallest members of these families don't have a PLL. The Igloo, ProASIC 3, and ProASIC 3L families don't have any other embedded features. The SmartFusion SoC FPGA family has 1 or 2 PLLs, a hard external memory controller that supports synchronous SRAM, pseudostatic SRAM or PSRAM, and NOR flash memories, a 100 MHz ARM Cortex-M3 microcontroller and peripherals, and analog blocks containing 2 or 3 analog to digital and digital to analog converters. Here's a summary of the embedded features in the low-density and mid-range families. Igloo 2 and SmartFusion 2 have between 11 and 240 math blocks for implementing DSP functions, 2, 6, or 8 PLLs for clock frequency synthesis, and transceivers that operate between 1 gigabit per second and 5 gigabits per second with built-in PCI Express Gen 2 endpoint support. Both families have a hard external memory controller that supports DDR2, DDR3, and LPDDR memories. Soft processors, based on the RISC-V instruction set, are available for Igloo 2. SmartFusion 2 includes a hard 166 MHz ARM Cortex-M3 microcontroller and peripherals. PolarFire has between 336 and 1,480 math blocks, 8 PLLs and 8 DLLs for clock frequency synthesis and phase adjustments, and transceivers that operate between 250 megabits per second and 12.7 gigabits per second with built-in PCI Express Gen 2 endpoint or root port support. A soft external memory controller that supports DDR4, DDR3, and LPDDR3 memories is available, and soft ARM Cortex-M1 or RISC-V cores are available for PolarFire. Finally, consider if the design requires any other attributes, such as Live at PowerUp. Is the design performing system management functions that can't wait for an FPGA to be configured? Low power. Is the design being deployed in packaging that would make it difficult to add a heatsink or a fan for cooling? Or is the design in a space-limited enclosure that requires small packaging? These are some of the considerations that can help you select the correct FPGA for your design. Refer to the course syllabus for links to additional information.
Okay, well, I see some questions here. Let's see, here's one. Somebody wanted to know, are there USB IPs? We do not have a USB IP that was created by Microchip. We have 2 classifications of IP. One is IP that we call direct cores that are created and supported by Microchip, and then we also have a number of partners that we work with. I don't recall off the top of my head if we have a partner that has developed a USB IP core. You can check on our website on our IP page. The Smart Fusion and Smart Fusion 2 devices have a hard, I'm sorry, the Smart Fusion 2 and PolarFire SoC devices have a hard USB controller. And there's a question somebody asked, what's the difference between hard and soft implementation? So when we say hard, we mean it's actually implemented as an ASIC, and you don't have to program anything. It's like an ASIC with an attachment that allows you to put logic in the FPGA fabric. We talked about hard and soft processors as well. So our SoC devices have what we call a hard processor, meaning that it's implemented as an ASIC. And then we also offer some IP cores that are soft processors that you could put in the FPGA fabric of an FPGA device like Igloo 2 or PolarFire.
Okay, as we have seen, these devices are all, not all, but they're quite powerful, and you need good tools to build an application. Shall we go on, continue with the presentation about the tools?
Let's see, I just saw one or two other questions here. Somebody asked, is there one flip-flop per logic element? Yes, that's true. And I think that pretty much covers it. So we might as well move on.
Okay.
Let's look at the FPGA design flow. The FPGA design flow starts with design capture. FPGA designers typically use a hardware description language to describe their designs. The HDL description is simulated to verify the functionality is correct. The synthesis step converts the HDL description into a structural netlist targeting a specific FPGA family. Place and route assigns the gates in the structural netlist to a location on the FPGA die and makes connections. Timing and power verification confirms the design objectives are met. Post-layout simulation can be used to verify the timing requirements are met. After verifying the timing and power requirements were met, the FPGA is programmed. FPGA designs are typically implemented using a hardware description language such as VHDL, Verilog, and System Verilog to describe the behavior of the system. HDL descriptions can be simulated and synthesized to produce a netlist containing gates for the target FPGA family. Some designs may be captured using a block-based approach with vendor-specific intellectual property cores and tools. This is an example of a description of a 4-input AND gate in VHDL and Verilog. In the VHDL description, I have the line Q is assigned A and B and C and D. In the Verilog description, I have assigned Q equals A and B and C and D. So I'm describing the behavior of a 4-input AND gate. Here's a second example. In this case, a 16-bit multiplier written in VHDL and Verilog. In the VHDL description, I have the line Q is assigned A times B. In Verilog, I have assigned Q equals A times B. So I'm describing the behavior of my circuit. I haven't instantiated any gates to implement my multiplier. Using an HDL description makes designs portable because the same description can be used to target different technologies. It's also easy to make modifications, such as changing the port width from 16 bits to 32 bits. The synthesis step converts the HDL description to logic gates. So here's my description of my 16-bit multiplier in Verilog. And after synthesis, I would have a netlist containing gates from the target FPGA family. In this case, PolarFire. The place and route step takes the cells in the netlist from synthesis, places them on the FPGA die, and makes the interconnects. When it's finished, it calculates the timing information based on the placement of the logic. So the cells in the structural netlist are placed on the FPGA die. This is a picture of a PolarFire FPGA die. The dark blue boxes are locations where logic's been assigned. I mentioned simulation earlier. There's different motivations for simulating in the FPGA design flow. We can simulate the HDL description during design capture to confirm that the description matches the design functional specifications. After running place and route, we can simulate to confirm that the design meets the timing specifications. There's many simulators available. Some of the popular simulators are ModelSim and QuestaSim from Mentor Graphics, which is now part of Siemens, and ActiveHDL and Riviera Pro from Aldec. This is an example showing functional simulation for my 4-input AND gate example. I'm showing a wave window from the simulator, and you can see the 4 inputs A, B, C, and D, and my output Q. The output Q goes high when all of the inputs are 1, and goes low when one or more inputs goes low. So this shows my Verilog description matches the functionality of a 4-input AND gate. Programming configures the FPGA. SRAM-based FPGAs typically need an external flash memory device to hold the bit stream. When the board is powered, the flash memory is read and the FPGA is configured. Microchip's flash-based FPGAs have a non-volatile programming element that is programmed directly, so no external flash memory is required.
The tools, I have worked with those tools in the past. It was always required a very heavy computer to get it all done in a reasonable time. I suppose that is still the case.
Well, we're working to improve the place of route times with every release, and I think they've come a long way. But at the same time, the densities are increasing too, so that can make it more of a challenge for the software. We do recommend at least 16 gigabytes of memory, and having a lot of memory is real important for having shorter place and route times. Let's see. I see a question. Does the compiler automatically implement a DSP block? So for the families that have the math blocks, that would be Igloo 2, SmartFusion 2, PolarFire, and PolarFire SoC. If you wrote a Verilog or VHDL description of a FIR filter or maybe a fast Fourier transform, then the tools will automatically use those math blocks to implement the multiply accumulate functions that are needed to implement that type of functionality.
Can the place and route take advantage of a GPU?
No. We our place and route software would just use the processor that's in your host PC or Linux workstation.
Okay. There was a question about development boards. We have a video about the development board, but do you have other development boards than the one we are going to see?
Yeah, there's actually several different development boards, and it depends on the families that you're looking at, the third, the fourth, or the fifth generation devices. But we have boards from Microchip, and there's also our distribution partners that have created boards for those families as well.
Okay.
If you look on the website under the FPGAs, you can see development kits, and it will show you all the different development kits that are available.
Okay, I see someone posted a link in there.
Somebody asked, "Do your FPGAs require strict power supply sequencing for the I/O blocks?" No, our power supply sequencing requirements are really non-existent. It's very simple. We just have a boot sequence with the device that will look and see when the core voltage hits a certain threshold, and when the I/O banks hit a certain threshold, and then the device will be up and operational.
Okay. Anything more that we can add
That's
right
one.
now?
Somebody
Or
wanted to know if there was any open source tool chains compatible with Microchip FPGAs. Um, Not exactly sure what you're looking for there. We do have development tools, and we have a free development tool set that you can get that supports many of the devices and all of the families that we've talked about. We also have some development tools that are available for purchase, but we do supply free software that includes all the steps that you would need to implement your design, simulations, synthesis, place and route. and so on. So what are the software tools to implement a VHL Verilog design and program microchip parts? If you were using our tool set that supports all of our families, our tool set is called Libro, and it includes the Model Sim simulator, and it includes Simplify Pro for synthesis. You could use other tools if you wanted to, if you went to a vendor and purchased tools directly, but those are the tools that are bundled with the tool suite that we provide. I think that's all I see here.
Okay, well then let's move on to the development board.
Let's take a look at the Hello FPGA kit. The kit consists of an LCD display, the Hello FPGA board, and a camera sensor board. The kit connects to a host PC via a USB 2.0A to Mini B cable to provide power and communication with the host. The Hello FPGA board is based on the Microchip SmartFusion 2 SoC FPGA with an ARM Cortex-M3 microcontroller. An external 50 MHz oscillator provides clocking. The board has 8 MB of SPI flash memory and 8 GB of DDR3 memory. 3 LEDs and 3 switches are provided for developing applications. The board includes a PIC32 microcontroller that is used to program the SmartFusion 2 FPGA, monitor power, and general purpose functions. There's a JTAG header for developing Cortex-M3 applications, and a PIC kit header for developing PIC32 applications. A USB 2.0 connector provides power for the board and communication with the host PC. There's an I2C, SPI, and UART interface between the PIC32 and SmartFusion 2 FPGA. There are 2 LEDs for developing PIC applications or debugging. The kit features expansion headers, Arduino, and microbus connectors for flexibility when it comes to prototyping. The Hello FPGA kit is designed for beginners and enthusiasts. It's ideal for developing control logic and data acquisition, image processing, signal processing, and artificial intelligence applications. The kit includes several demos provided by Microchip. The DSP demo highlights the SmartFusion 2 features for implementing digital signal processing. In this demo, a FIR filter is implemented in the fabric for low-pass, high-pass, bandpass, and band reject filtering operations, and a fast Fourier transform is performed on the waveforms. The Hello FPGA GUI is used to generate the filter coefficients and input signals and plots the input and output waveforms. Here's the Hello FPGA GUI. In the filter generation section, I can choose the filter type as low pass, high pass, band pass, or band stop. I'll just leave the default of low pass. I also have different filter windows that I can choose. And I can enter my high cutoff frequency. I'll change this to 30 megahertz. And I can generate my filter. Down here, I can set up my input signals. Let's put in a 10 megahertz signal and a 55 megahertz signal and generate our waveforms. On the filter input tab, you can see the signals and the frequency spectrum, my 10 megahertz, my 55 megahertz signal. I'm going to click start. And now I'm going to look at the filter output, and I can see I only have my 10 megahertz component now, and here's the waveform. I can look at the text viewer, and I can see the numerical values for the graphs that were plotted in the filter input and filter output tabs. If I click auto sweep, the GUI automatically sweeps one of the input frequencies through a range of values and sends to the FPGA to perform filtering operations. The power measurement demo displays the power consumption of any of the demo designs and also demonstrates the use of the SmartFusion 2 Flash Freeze ultra-low power mode. The Power Graph tab is available for all the Hello FPGA demos. It displays the power consumption of the demo design. Pressing the Flash Freeze entry button enables the SmartFusion 2 Flash Freeze mode. Flash Freeze is an ultra-low power mode that suspends the operation of the FPGA fabric while retaining the states of the flip-flops and the memory contents. The GUI displays the power consumption while in the flash freeze mode. Pressing the flash freeze exit button restores the device back to normal operation. The GUI displays the flash freeze exit to FPGA functional time. In the image processing demo, video captured from the camera is displayed on the LCD module. The FPGA processes the image to adjust contrast, brightness, and color balance using inputs from the Hello FPGA GUI. Here's the Hello FPGA GUI for the image processing demo and the LCD module. Using the sliders, I can adjust the contrast, the brightness, the red color balance, the green color balance, and the blue color balance. I can make multiple adjustments simultaneously. The signal processing is done in the SmartFusion 2 SoC FPGA. The Artificial Intelligence demo shows SmartFusion 2's machine learning interface capability by performing real-time handwritten digit recognition. The user points the camera to align the green box around a digit in the GUI with the green box in the LCD. The recognized digit is displayed on the LCD and on the left side of the GUI window. 3 digit sets are provided to allow testing with different fonts. The Hello FPGA Kit is an ideal kit for end users with low to medium FPGA experience. The demos that are included get you up and running quickly. Please refer to the course syllabus for links to additional information on the Hello FPGA Kit. In the next video, I'll demonstrate how to create a design for the Hello FPGA Kit from scratch.
Okay, well, for the next video to see this design, you have to move over to the Microchip University because we have come to the end of our presentation. Well, now let's move on then to the Q&A session. Let's see if there are some more questions. We already answered a lot of questions. See if there are any more left. It's almost 5 o'clock also.
I saw some questions about general availability. I personally don't have any information on the general availability. I would recommend that you check with one of our salespeople in your area, a Microchip salesperson, or one of our distribution partners to find out exactly the lead time for the particular device that you're looking at. Somebody wanted to know, can we build a soft RISC-V core with the Hello FPGA kit? You can. It has a small device on it. It has a device with 10,000 lookup elements. So you're squeezing a lot of logic in there, but it can be done. I've done it myself.
Here I found an unanswered question. Is there an audio codec?
I'm not sure what they were referring to there. We don't have an audio codec built in. Somebody asked USB with FTDI JTAG serial. In the programming steps, you saw we showed a JTAG port and we also showed a PIC microcontroller. There's multiple ways you can program our devices. One way we can program is through the dedicated JTAG port. And we have programmers that would allow you to connect to the JTAG port. In some cases, we use a USB connector, and then we have one of the FTD devices to convert USB to serial. You can also program with a processor or a microcontroller on the board as well.
Okay, here is another question. What is the biggest FPGA that is supported by the free tools?
I would say the biggest device, if you're looking at logic density, would be one of the PolarFire 300s. What we've done is we took the devices that are on our development kits and we put them in the free software. So our free Libro tool supports the MPF 300 in in the package combination that's on either our PolarFire evaluation kit or our PolarFire development kit. And in addition, there is a PolarFire SoC kit that has a 200,000 logic element device along with the 5-core complex with all the peripherals and everything, and that's included in the free version of the software as well.
Here's a related question. What are the costs and limitations?
The licensing varies depending on the type of license you get and the duration, the term of the license. So we have node lock licenses for PCs. We have floating licenses for PCs and Linux. So it all varies. And then we also have purchase licenses that support all the products, and we have purchase licenses that support a subset of the products. And we also have purchase licenses that are perpetual licenses. So we have a license selector guide that you can download from our website, and it allows you to put in a specific die and package or just the family that you're looking at considering designing with, and then it will tell you the license that's needed, and it has the information in there as far as the cost.
Okay. Another question, are there any tiny FPGAs to add to a battery-powered device?
Any tinier FPGAs to add to a battery-powered device with a PIC micro. If you're looking for something very small, I would suggest you would want to look at the 3rd generation devices, either ProASIC 3, or if you're concerned about power, we have the family that's called the Igloo family. And the Igloo family is architecturally the same as ProASIC 3, but it's designed slightly differently so that we have lower power. We have a slightly different uh, uh, technology that was used when we built those, and we have much lower leakage with the Igloo family than we have with ProASIC 3. So if you're looking for something small, I would consider either ProASIC 3 or Igloo. And if you're really concerned about power, then Igloo would be a good one to look at because it has a very unique power saving mode that we call Flash Freeze that allows you to basically suspend the FPGA operation to save power and then quickly power it back up again.
This reminds me, I think in the past it was, of course, totally illegal, but I think it was an Igloo device used to crack Nintendo Wii game consoles. It was a really small application.
I don't recall off the top of my head all the details on that now, but people are obviously always trying to, uh, crack into practically anything, and that does bring up the idea of security. We have very robust security features in the 4th and 5th generation FPGA families, Smart Fusion 2, Igloo 2, PolarFire, and PolarFire SoC.
Okay. Well, one last question. Can you force the external I/O via JTAG ISP programming to drive external hardware for board testing?
Force the external I/O via JTAG ISP programming to drive external hardware for board testing. I'm not quite sure what type of board testing you're referring to. We can use the standard JTAG method of testing boards so that you can do the scan chain and scan all the way through the device, make sure all the IOs are connected and that sort of thing. So we have a dedicated JTAG on all our devices that has an IEEE compliant JTAG tap controller. So we support the standard board testing using JTAG methods. It's also a method that we can use to program the devices. It's not the only method, but is one of the methods that you can use to program. I hope that answered
Okay,
the question.
that's not sure. I guess so. We have passed the hour. I think we should stop. So I hope you all found it useful and interesting. As I said in the beginning, this webinar will be available afterwards on the Elektor TV channel, where you can watch it as many times as you like, and pause it so to take screenshots. The goal is, of course, that you go now to the Microchip University website to take the course, the full course, and learn everything that there is to learn. and earn your certificates. The next Elektor webinar will be about embedded development and is scheduled for April the 14th, which is in about 3 weeks. So I hope to see you here again. Thank you, Tim. Thank you very much for doing this webinar with me, and thank you all for attending.
Thank you, Clemens. Thanks
Goodbye.
for the invitation. Thanks, everybody.